Let's dive right into this explainer. Today, we're unpacking something absolutely fascinating, the evolution of engineering power. We're going to explore exactly how ancient and medieval builders mastered some seriously advanced physics. We're talking concepts like torque, mechanical advantage, and kinetic energy, centuries before modern science ever even gave them those names. These weren't just primitive people stacking stones, you guys. They were brilliant engineers designing incredibly complex machines.
To really put this into perspective, I want you to imagine a Roman quinquereme warship. These things were massive, terrifying vessels, fully loaded with troops and artillery and weighing in at roughly 100 metric tons. Now imagine you're a 3rd century Greek engineer tasked with stopping an entire fleet of them. How in the world do you physically lift a 100-ton warship completely out of the water using nothing but wood, lead, and rope?
Well, the Greek historian Plutarch wrote down exactly what happened when the Romans tried to assault Syracuse by sea. He described how the ships were, quote, lifted clean out of the water into the air, whirled about and dashed against rocks or plunged stern foremost into the depths. It's a deeply terrifying image, right? The Romans were going up against a legendary weapon known as the claw of Archimedes. Now, the secret to the claw wasn't magic at all. It was pure, unadulterated physics, specifically torque. Torque is basically just the rotational force applied to an object, and the formula is beautifully simple: force multiplied by distance. By extending a massive wooden lever arm over the city wall and hanging a heavy lead counterweight at a short distance on the opposite end, Archimedes created immense mechanical advantage. The claw would drop a huge iron grapple onto the ship's bow, and simply by releasing that counterweight, it generated enough torque to hoist a 100-ton ship up to a 45-degree angle. It completely destabilized the ship until it just capsized.
And hey, if you think that's impressive, let's take a look at the offensive side of ancient engineering. Meet the Helepolis. It was a monstrous ancient Greek siege tower. This absolute beast was 130 feet tall, completely armored in iron plates, and weighed a staggering 160 short tons. But here's the crazy part. They didn't just drag it. It was moved by a massive team of 3,400 men, with 200 of them actually inside the tower, turning a gigantic capstan that drove the wheels using a mechanical belt drive. A belt drive. It completely shatters the illusion that ancient builders were technologically primitive. Act 1. The physics of siegecraft, from ancient torsion to medieval gravity. As we transition from antiquity into the Middle Ages, military engineers took these foundational concepts and evolved them into entirely new classes of machines. A perfect example of this is comparing the ancient Roman ballista to the 13th century springald. Both relied on torsion, which is the stored energy of tightly twisted ropes. But the Roman ballista used outward swinging arms, a design that was incredibly complex and required perfect precision to tune. The medieval springald, on the other hand, used inward swinging arms powered by tightly twisted skeins of silk or sinew. And what's really wild is that historians believe the rapid development of the springald was directly linked to the invention of the spinning wheel in Europe. The spinning wheel suddenly made winding those tight hair and sinew skeins so much easier. It's a great example of technology in one sector bleeding directly into another. But torsion definitely wasn't the only game in town. Let's look at the mechanics of the mangonel, also known as the traction trebuchet. Instead of relying on complex torsion springs that could easily snap or lose their tension in wet weather, the mangonel simplified the whole operation. It used a pivoting throwing arm resting on a pedestal. On the short end of that arm, a team of 20 to 100 human operators would pull downward with everything they had. This sudden, massive force whipped the long arm forward, utilizing raw leverage to violently fling a stone out of a sling. By the late 12th century, though, engineers looked at those exhausted human pullers and realized they could do a lot better. So they replaced the team of men with a massive pendulum counterweight. This single design tweak created the era's undisputed dominant heavy artillery weapon, the counterweight trebuchet. This machine could absolutely shatter castle walls from a safe distance. And the best part? It operated purely on the physics of gravity. Let's walk through exactly how this beast worked, step by step. First, operators crank up the massive counterweight, which stores up an immense amount of gravitational potential energy. Then, the trigger is released, and the counterweight simply plummets. This is where the magic happens. All of that stored potential energy is violently and rapidly converted into kinetic energy. It whips the long throwing arm upward and releases the projectile from the sling at terrifying speeds. It's just such an elegant yet totally devastating application of physics. Act 2.
harnessing nature, capturing wind and water.
War wasn't the only thing driving innovation back then. Think about what happens when medieval engineers apply these exact same principles of torque and leverage to capture the raw power of nature. They effectively spark an industrial revolution. We see this perfectly with water wheels. The older design is the undershot water wheel, which basically just dips its paddles into a stream. It gets pushed by the velocity of the water, but it maxes out at about 30% efficiency. Medieval engineers, though, perfected the overshot water wheel. By channeling an elevated stream of water completely over the top of the wheel and into specifically designed buckets, they weren't just using the water's speed anymore, they were literally harnessing its physical weight and gravity. This generated way more reliable, consistent torque to power their heavy machinery.
And in places where they didn't have falling water, they harnessed the air. Check out the aerodynamic ingenuity of the medieval windmill. They didn't just slap flat paddles onto a building. The canvas sails were specifically angled on a wooden lattice. When the wind hit that angled sail, the sail actually deflected the wind downward. And thanks to Newton's third law, every action has an equal and opposite reaction, the air pushed back upward against the sail, creating rotational torque. They were practically sailing the sky.
But obviously, a spinning water wheel or windmill doesn't do you much good if it's spinning at the wrong speed. Enter the concept of the gear ratio. Inside these mills, engineers use networks of wooden gears to control all that power. If a massive water wheel cog drives a much smaller gear, which is called a pinion, the rotational speed drastically increases, even though the overall torque decreases. This genius trick allowed millers to take a really slow, powerful river current and step up the speed so their heavy millstones could spin at the rapid, optimal rate for grinding grain.
We also see this kind of extreme leverage being used to build the iconic skylines of Europe. Those massive soaring cathedrals you see, they were built using treadwheel cranes. Human operators basically walked inside a giant wooden hamster wheel. The lifting force they generated was brilliantly amplified by a mathematical formula. The total weight of the operators multiplied by their horizontal distance from the center, divided by the radius of the axle. Put simply, just a few people walking inside a large wheel could generate enough mechanical advantage to lift multi-ton blocks of solid limestone hundreds of feet into the air. Now, as these machines got bigger and heavier, their control mechanisms had to get a lot smarter. Take pile drivers, for example. These were used to smash giant wooden beams deep into riverbeds to create bridge foundations. You use a crank or a windlass to haul up a heavy iron ram. But here's the problem. How do you drop that massive weight without the lifting crank violently spinning backward and breaking all the operators' arms? Well, a 15th century engineer named Mariano Toccola designed an absolutely ingenious release mechanism. He used a specially shaped hook to lift the ram. When it reaches the very top, a roller on the back of the hook strikes a wooden beam. This physically forces the hook to rotate, cleanly dropping the weight and allowing the windlass to just reset safely. It's a brilliant mechanical solution to a very dangerous problem.
Act 3. Precision and complexity. The machinery of time.
This is where the raw, brute power of siege engines and watermills transitions into something entirely different. Intricate, mind-bending precision. Behold the Verge and Foliot mechanical clock. This masterpiece was the world's first machine made entirely out of iron. Earlier water clocks had a tendency to freeze solid in the winter, so medieval monks and engineers desperately needed a reliable way to track time and the movement of celestial bodies. But to actually build a working mechanical clock, they had to solve a massive physics problem.
And here is that exact mechanical problem. A clock needs constant, steady power to tick accurately. The builders used heavy iron weights tied to ropes to pull the gears. But, as physics dictates, a freely falling weight accelerates. It falls faster and faster the longer it drops. If your power source is constantly speeding up, keeping accurate, steady time is physically impossible. The solution they came up with is arguably one of the greatest engineering inventions in human history, the escapement mechanism. It's exactly what gave us that legendary tick-tock sound. Here's how it works. As the falling weight pulls a toothed gear called the crown wheel, one of those teeth strikes a small metal flap called a pallet, which is attached to a vertical rod. This completely stops the wheel, but the impact pushes the rod out of the way, letting the wheel briefly escape. Then, as it spins again, a bottom pallet catches the next tooth, stopping it all over again. Tick, stop. Tock, stop. To quote the source material directly, the escapement operates by subdividing the fall of the wake into a series of discrete time intervals of equal duration. Think about that. It is literally taking continuous gravitational acceleration and slicing it into equal, manageable, identical chunks of time. It is an absolute masterpiece of precision engineering.
This whole era of precise mechanics really culminated in devices like the printing press. Johannes Gutenberg didn't just invent movable type out of nowhere. He basically synthesized centuries of mechanical knowledge into one machine. He took the concept of the screw, an ancient machine used to convert rotational torque into downward linear force, and combined it with a sliding bed and a clever system of levers. This allowed the press to apply immense, yet perfectly even pressure onto a fragile sheet of paper.
And that brings us to the end of our explainer today. We've journeyed all the way from using simple levers to capsize 100-ton warships, right up to using tiny iron pallets to slice time itself into seconds. So I want to leave you with this final question. Which of these medieval mechanical marvels is still silently turning the gears of your modern life today? From the camshaft sitting in your car's engine to the massive gearboxes inside modern wind turbines, the mechanical brilliance of the Middle Ages absolutely remains the foundation of our modern world. Thanks so much for exploring this with me today.